Today we're going to cover the rest of section 2.7, standard enthalpy changes, 2.8, standard enthalpy of formation, and 2.9, the temperature dependence of reaction enthalpies. Continuing from section 2.7, let's talk about 2.7b, the enthalpies of chemical change. This is a concept that you are familiar with. You've seen this before in general chemistry. So this should be sort of a review for you. So let's revisit this concept. Suppose we have the thermochemical equation . Methane reacting with oxygen, yielding the products carbon dioxide plus water. What makes this a thermochemical equation is that we have the reaction accompanied by the reaction enthalpy. Like that. So together, these two components make up the thermochemical equation. This is a combustion reaction. We have a substance that is reacting with pure oxygen, which yields carbon dioxide and water. Here, delta R H naught, like that, with a line through it, is called the standard reaction enthalpy. And the standard reaction enthalpy is for pure separate reactants in standard state, as we've defined last time, and pure separate products in standard state. For the general reaction, that is written like this, where the lowercase letters are the coefficients of a balanced chemical equation, and A, B, C, and D, capital A, B, C, and D, refer to the pure substances. We can sum up the enthalpies, the standard enthalpies of the various substances to calculate the standard enthalpy of the reaction. So what we do is we multiply the number of moles of a pure substance with the standard enthalpy of the pure substance. So we're in moles here. This thing is, this quantity is given in probably kilojoules per mole. So what you get is a cancellation of the units of mole, and so your reaction enthalpy is going to wind up being in terms of just joules or kilojoules. So we have, we add up the products like that. And from the sum of the enthalpies of the products, we subtract the sum of the enthalpies of the reactants. Just like how you've done it a couple years ago. Or, to write it more succinctly, we can just use the summation, the sigma notate, or the sigma, the capital sigma, to denote summation. So for any reaction, no matter how many products or how many reactants you have, you take the sum of the standard enthalpies of the products and from that you subtract the sum of the enthalpies of the reactants. I should get rid of that S there. There. So for each product you have, you multiply the number of moles of that particular substance by its standard enthalpy. And then nu represents the coefficients. We can denote the standard enthalpy of combustion like this with the subscript C. So for just a general reaction you use a subscript R, but if you have a particular kind of reaction, if you have a hydrolysis or a combustion, you can denote that particular type of reaction with some sort of a subscript that symbolizes what that particular reaction is. So this is the common form. This is the common way that we notate the standard enthalpy of combustion. And what this is the change in enthalpy, the standard change in enthalpy for the combustion of 1 mole of substance. So the standard enthalpy of combustion centers around the substance that is undergoing combustion. So in the case of this reaction, it's all about the methane. So this represents the change in standard enthalpy for the combustion of 1 mole of methane. So when you are writing a combustion reaction, please be sure to make sure that the substance that's being combusted has a coefficient of 1 in front of it. That would mean that you may wind up with coefficients that are like 7/2 oxygen, or you may wind up with fractions for the other coefficients, which is okay. So that brings us to Hess's law. Hess's law is a law that tells us about how we can add up enthalpies in order to express the enthalpy of maybe a larger reaction. So Hess's law, so let's just define what Hess's law is. Hess's law is the standard enthalpy change for an overall reaction where the standard enthalpy change is equal to the sum of standard enthalpies of the individual reactions. An excellent example is example 2.5 of how this works. The idea is that you can manipulate the equations for all of the individual reactions in such a way that when you add up all the reactions together, they will sum up to the overall reaction. And in doing so, in manipulating these reactions, you're going to have to change delta H for all of these reactions along the way. And so the rules are like this. Number one, if for some reaction you have a standard enthalpy of delta R H, then if you were to swap the products to the reactant side and the reactants to the product side, you must change the sign on the standard enthalpy. The second rule is if the coefficients in the reaction are multiplied by a factor of n, then what you need to do is multiply the reaction enthalpy by that same factor. I'm not saying that n needs to be an integer. It can be a fraction. But just be sure that if you're going to multiply the entire chemical equation by that factor, that you must multiply the accompanying standard enthalpy by that factor as well. That brings us to 2.8. Standard enthalpies of formation. Denoted by this subscript F after the delta. The standard enthalpy of formation of a pure substance is defined as the standard enthalpy of reaction for the formation of 1 mole of that pure substance from its elements in their reference states. So, first of all, let's define what a reference state is. The reference state of an element is simply the most stable state or most stable form of an element at a specified temperature and of course that's usually room temperature. And at standard pressure of 1 bar. Let's look at some examples of reference states of elements. Well, what would be a reference state for mercury at 298 Kelvin? So mercury, as we know, at room temperature is a liquid. So the reference state is denoted like this with an L. So that's the reference state for mercury. What about oxygen? What is the most stable form of oxygen at 298 Kelvin? It is as a diatomic molecule, O2, not as ozone. Chlorine, its most stable form, oh, I should put a G here, it's a gas, is as a diatomic molecule in the gaseous state. Carbon, its most stable form at 298, come on, go away. Okay, here we go. Is solid, and in particular, well, there are several different forms of solid carbon. You've got buckyballs, you've got diamond, but actually the most common stable form is graphite. So we do need to denote the reference states in terms of its physical state, solid, liquid, gas, and also in terms of its, well, molecular composition, I guess. Well, let's look at what the heat of formation, the standard heat of formation is for benzene. Well, first of all, let's look at what the thermochemical reaction is for benzene. So we are creating benzene from its elements in their most stable state. So we have 6 carbon atoms, and we have 6 hydrogen atoms. Now hydrogen in its most stable form at 298 Kelvin is as a diatomic molecule, and the resulting reaction between these two elements gives us benzene, and its most stable state is as a liquid at room temperature. The standard enthalpy of reaction in this case is equal to the standard enthalpy of formation of benzene, which is equal to 49.0 kilojoules per mole. Now, benzene is not an element, and it is not, even though it's in its most stable state, it is not an element. Therefore, it has an enthalpy of formation that is not 0. But the enthalpy of formation of elements in their reference states is 0. So you may be wondering, well, if the enthalpy of formation of carbon in its reference state is 0, and that of hydrogen in its reference state is 0, how is it that when you add these together, they give you a compound that has a heat of formation, or an enthalpy, a standard enthalpy of formation, that is not 0? That doesn't make sense, because, shouldn't there be some kind of summation thing here? I mean, shouldn't this, the enthalpy of the products, equal the negative of the sum of the enthalpies of the reactants? Well, in this case, in terms of the enthalpy of formation, we have to consider the enthalpies of bond breaking and bond making in order to determine what the enthalpy, the standard enthalpy of formation is of a new compound. So all of that contributes to the enthalpy of formation of a compound, of a compound that is not monatomic, that is not elemental. Does that make sense? So to say it again, what constitutes the standard enthalpy of formation of a compound is all of the enthalpies involved in bond breaking for the elements and bond forming between the atoms of the elements in order to make the compound. So if the enthalpy of formation of the elements in the reference states is 0, then we should know that for all of these compounds listed here, the enthalpies of formation are 0. So for mercury as a liquid at 298 Kelvin, that's 0. The diatomic molecule oxygen in the gas state at 298 Kelvin is 0. However, the enthalpy of formation of ozone is not 0. That brings us to what is the enthalpy of formation for ions in solution? What we do here is we need a reference point, and it's set arbitrarily, but it makes sense how it's set. And it's set by just assuming that the standard enthalpy of formation of the hydrogen ion in solution is equal to 0. And all of the other enthalpies of formation for all the other ions are based on this reference point. So let's say we want to know what the enthalpy of formation is for the silver ion. In solution. And let's say that we have measured the enthalpy of formation of hydrobromic acid. And that was measured to be negative 122 kilojoules per mole. Okay, so we measured that. And we know certain things about hydrobromic acid, and that is we can first, if we write the thermochemical equation for hydrobromic acid, for the formation of hydrobromic acid, what we have let me just finish writing this. We can deduce certain things from this. Well, number one, we know that the reference point, let me make that into an R. Our reference point is set arbitrarily for the heat of formation of the hydrogen ion. So one thing we know is that this is equal to 0. We know this was measured to be negative 122 kilojoules per mole. Okay, well, what does that mean for the standard enthalpy of formation for the bromide ion? Both sides need to be equal to each other. So we've got 0 plus this equals negative 122. Well, that means that this standard enthalpy of formation must also be negative 122 kilojoules per mole, because that's 0. So both sides equal each other. So using that information, we can then measure the standard enthalpy of formation of silver bromide and from there we can figure out what the enthalpy of formation is of the silver ion in solution. So oh, I forgot something. So the heat of formation of the silver ion in solution must be equal to the enthalpy of formation of silver bromide that was measured minus the enthalpy of formation of the bromide ion as calculated from the thermochemical reaction above. And to illustrate how I got this equation, well, let's consider the sum of the two ions to make the ionic compound. So this side must, the enthalpy of this side must equal the enthalpy of the other side. So we just subtract the enthalpy of the bromide ion from both sides, and then we can solve for the enthalpy of formation of the silver ion by itself. So again, finding the reaction enthalpy well, maybe I should say we can find the reaction enthalpy for a chemical reaction not only from the enthalpies of the various compounds that are the reactants and the products of the reaction, but we also can find the reaction enthalpy using the enthalpies of formation of the products and reactants. And this looks exactly the same as what we have seen in 2.7 B. So the standard enthalpy of a reaction is equal to the number of moles of each product multiplied by the respective enthalpy of formation of that product minus the same for the reactant side. So you sum each one of these components for the product, and from that you subtract the sum of the enthalpies of the reactants. And finally today, we're going to talk about the temperature dependence of reaction enthalpies. Okay, what if you want to know what the standard reaction enthalpy is of a chemical reaction, but at a different temperature? You can have a standard enthalpy at a different temperature, as long as the pressure remains at 1 bar. So the standard enthalpy again is at a specified temperature. That specified temperature doesn't have to be 298 Kelvin. It could be at any temperature. And in particular, when we talk about what the standard enthalpy of a reaction is at a different temperature, that means at a temperature that is not 298 Kelvin. Which is where we usually calculate the standard enthalpy. Recall the following. The change in enthalpy is equal to the integral of the heat capacity at constant pressure well then we have the enthalpy at the second temperature minus the enthalpy at the first temperature. You know what, maybe I will call this initial and final. Okay, there we go. All right. Is equal to, again, this integral. And because I'm only interested in the enthalpy at the final temperature, I'm going to move the enthalpy of the initial temperature over to the other side. So I add that enthalpy to both sides, and I get the final, this equation. Now, like the fact that we have the change in standard enthalpy of a reaction as being the sum of the enthalpies of the products, and I put a bar over there to show that we're talking about the molar enthalpy. And we have the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. We can also, for the products of the reactants, we have a change in the standard heat capacity at constant pressure. That is, calculated in the same manner. And these values are provided so that you can calculate this change in heat capacity. And what this value is called is this thing is called the standard heat capacity change. For the reaction, which is given in joules per mole Kelvin. And considering that we have reactants and we've got products, we can actually take this equation for the reactants and this equation for the products, and you subtract the product value from this equation. I'm sorry, you subtract the reactant value for this equation from the product value of this equation, and you wind up with Kirchhoff's law. Which gives us the standard enthalpy for a reaction at the final temperature based on what we know about the enthalpy of the reaction at the initial temperature by adding the enthalpy of the reaction at the initial temperature to this integral. Now, fortunately, for small temperature ranges, we can treat the standard heat capacity change as a constant. And if we do that, then this becomes a constant. It gets moved to the outside of the integral, and we are just simply left with the following linear equation. And again, this is being treated as a constant. And that's it. And I will see you on Friday. Probably tomorrow though, too. Take care.